Okay, very happy to see that. Oh, Salim also here. I saw him online. So, who we are and what are we doing and what is the goal for today? It is a call. It is a course in computational chemistry. We do set up a goal to model and predict properties of materials and molecules, and we are on the third chapter going over density functional theory method for compute electronic structure. Objectively, our lectures are a little ahead and our labs are noticeably behind. So we are about 2 labs behind, and maybe I need to migrate some lab materials to the lecture, or next lab we may want to try to meet for a little longer than 2 hours. So by now you do have general idea of how density functional theory works for electronic structure, and you already have completed the homework with density of states. If you haven't submitted this postponed homework by now, please try to do your best and complete it before the actual beginning of tomorrow's lab. On tomorrow's lab, we will go over new material, and there will be absolutely no time to return to this important thing. I didn't answer one of the questions in the emails, but I'm going to do better and answer questions more actively. So please send technical questions if you face it. If you see problems with login or doing some practical steps, do not hesitate to share screenshots of your situation when you need help. And also, the class attendees are not competitors. Class attendees are more like colleagues and partners. So please try to help each other and consult with each other as well. So we need to go over these barriers together. I'm going to show all details in slides, so do not worry if you do not see them right now. I will repeat things that are most important. For the fundamental part of the density functional theory, we may need maybe one more section, the explicit expressions for functionals. And this time I'm going to give it to you with understanding that typically applied researchers, applied scientists who are focused on applied research do not design or operate with these equations. They are typically hidden in the input files of the software. Hi Salim, nice seeing you. I will partially cover it today and maybe keep showing some of the functionals on next lectures. Other than that, you are approaching the level of being certified experts in density functional theory. You know theorems, and you know the Kohn-Sham algorithm. So in academic, in the abstract part, we are already close to completing this chapter and go into more advanced sections. But since our practical skills are a little behind, I will try to bring in some components, some practical components to the lectures. So the fundamental component will be explicit expressions for functionals, and applied components will be related to observables. One of the most important things will be how to extract absorption spectrum, interaction of light to matter, from the output of WASP, and this will be main subject of our lab tomorrow. Plus, we will try to plot orbitals. Another section, another part of the practical part, which is more appropriate for labs, but I need to bring it in the lectures, is charge and spin multiplicity, which you have covered in Gaussian, and we will need this time to cover it in WASP. And there are some material behind these practical steps. Excuse me, they will be reasonable to show in the lectures. And there is a most important part for the projects, molecular dynamics, which is I can bring something to one of the next lectures, but it is so simple and basic, and it overlaps with chapter 1 in our lectures that it will be maybe 1 or 2 slides. Okay. So I'm going to show slides, and if you do have questions, please attract my attention by voice, because I may miss if you're showing some signs. Okay. So we are considering theories and software, and we will need to discuss observables before we go to practical aspects. I appreciate very much your collective effort in selecting the subjects for presentations on practical skills of WASP. So I do not see.
I think
yes, Salim.
I think I would like to choose the thermal heating project.
Excellent, excellent. It was the only one subject without.
Yes, I see that.
Okay, so confirmed.
All right, thank you.
So for WASP input, we completed everything, and I think this subject is clear. For WASP output and density of states, we also focused on it. The orbitals, the plotting of orbitals will be very similar to plotting of the charge density, what we did in the last 10 minutes of the previous lab. But I strongly encourage everyone to make sure that you do have the visual molecular dynamics software on your laptops. I did share some YouTube videos how to download, set up the password, and install. If this installation doesn't work on your laptop, feel free to send email to me or to each other. Or if you send it to me, I can share it with those who have confirmed that it has been installed. But it is a really important tool. I do have a backup plan for those who will be not able to install it, but it will be a very complicated and unpleasant thing. The using VMD is really cool. Yang Chao?
Yes.
Do you have this software on your laptop?
Yes.
Excellent. Then at least our presentations are safe. But
okay, no problem.
Good. But it is very encouraged that everyone will have it. Momentum dispersion. Amir may want to consult with me in person because I'm not sure if we have time in class to cover it. I can briefly do it, but it will be an heroic feat to prepare in private. But it is a very important subject, and there is a record from 6 years of teaching this course. Anyone who selects to present this subject is publishing a paper half a year later based on class material. So you're in a good company. This subject is important but not challenging. I guarantee we will cover it maybe in a week from now, not the coming lab, but the next lab. And it will be associated with spin-polarized dose as soon as we, so probably it is in 2 weeks. Spectra. This will be a subject of our tomorrow lab. So orbitals and spectra, it is what we are going to cover tomorrow. And thermal heating and movies, probably I do have a goal that we complete all practical steps in VASP in 2 weeks, coming week and second week, and then do presentations. Otherwise, it will be big danger for the course. So ideally, it will be really cool if presentations will happen on April 8th, which is quite early, and especially for those who are presenting second half of subjects, it will be a stress. So basically, on Wednesday, in a week, on a second Wednesday from now, you pick up the skill, and next morning you present. This will be really great. If it is absolutely non-possible, we'll consider some options, but please prepare your internal strengths for this. Okay.
Hi, Dr. Kelly.
Yes.
So we will, for my topic, we will use the VMD or other software to create the movies or something.
Yes, VMD.
Okay.
Creating movies is absolutely not a problem. The little challenge, well, it is not a challenge, but it is an important practical skill, is how to compute molecular dynamics. And then generating output in form of movies is quite easy.
Okay.
Okay, so thank you for reviewing it together. What do we have next? So the equation that I'm trying to put in yellow box is probably most important fundamental equation of today's lecture, and it is important from theoretical side, but I'm not going to speak much about it. Just bring into your attention that there are a lot of ways to express total energy as a function of density. And if you were enjoying the work with Gauss-View and Gaussian, you may remember that if you select density functional theory in the methods, then there is a second menu to select functional. And we were selecting B3 lip, but in the drop-down menu, there were a dozen of other functionals. So all these selections in the drop-down menu are correspond to equation how to convert total density into total energy. There is a second DFT theorem that tells that if this equation is known, this equation does exist, and if humans will learn this equation, then ground state density will give with absolute precision ground state total energy. But the real situation is that humans do not know an equation for density functional. Humans know only approximations. And there is a competition in the community who will find this equation in the best possible way. By finding this equation more or less precise, one can approach better and better the total energy of a given molecule. But and there is a group of people who are competing, proving theorems, doing a lot of theoretical effort to express these formulas in the best possible way. We are not going to dive into this activity very deep, because if you go this direction, it will keep you involved for the whole life. It is really exciting and useful activity, but we are setting up applied research as a primary goal. The simplest approximation is that total energy does depend on the density in a single point, in the local point R. You do remember that when we were starting density functional theory, we considered Thomas Fermi theory, where total energy is equal integral over density into power 5/3. There is a way to prove, which we are not going to do right now, that if one changes the power 5/3 into power 4/3 and use this functional in our auxiliary world where there are no electron-electron interactions, and then impose transformation from here to there, that the power rho into the power 4/3 will give very reasonable results qualitatively agreeing with a lot of experiments. This expression depends on density in a local point, in a point of space R. And we just use integration over all points of space, and density is used only in one point of space. Therefore, it is local in space, it depends on density, and it is approximation. Therefore, it is called local density approximation. And this is maybe the only formula, the only expression that one can write on one slide. All other functionals will take several slides just to write this equation. And all other functionals are typically non-local. They use at least a gradient of a density. If we convert this power 4/3, which is equivalent to power 3/3 times 1/3, and this can be expressed in terms of functional integration. This just a second. So rho into the power 1 times dr is equivalent to increment of the density, and in terms of functional integration, it will be integral of the rho into the power 1/3. And then if we implement functional derivative, then functional derivative of the total energy over density will be rho to the power 1/3. This is the potential that is used in the Kohn-Sham equations. And quite, yes?
But the equation of the energy was rho to the power 5/3, but when you make the energy density LDS, you make it 4/3.
Please repeat.
The first equation you just wrote at the top is the power of 5/3.
Yes, 5/3.
And
yes, just a second. Just a second. 5/3 is an equation for Thomas
Fermi.
Fermi, yes. Please continue.
And for the local density approximation for LDA, you write the energy in terms of density. So there is a 3/3 and 1/3 that makes 4/3.
Exactly.
Why is that?
We are not considering this. I'm not going to prove it.
Okay. Then is it a proof?
There is a proof, but I'm not going to show it.
Okay. So it's not from the Thomas Fermi?
No. It is independent proof.
Okay. Understand. Thank you.
Okay. So, and quite general expression for all density functional theory approaches is that energy is functional integral of the potential times increment of density. If we will have time today, or maybe on the next lecture, I will show how the local density approximation is generalized in a case of a spin. And then one will need to process, to introduce the parameter of spin polarization. So it was a little heads up. So we are expanding the lecture, what was lecture 22 many years ago, onto maybe on 3 lectures, because we need to expand time and practice more practical skills before we go to the manual on presentations. For the next weekend, I am suggesting a new homework that will summarize what we will complete during the coming lab. So first 2 sections are just copy pasting from the lecture. It's boring, but maybe will help you to revise the lecture. It will take maybe 5 minutes. And the section 3 is to plot orbitals for the oligomers that you have computed with VASP. So it is built on the accomplishment of the previous homework. Then section 4 will be to compute so-called oscillator strengths if for each of these models. And the oscillator strengths is a key part of the absorption spectrum, and I'm going to cover it with guarantee today and on the next lab. So oscillator strengths and absorption spectra for each of the oligomers. And here are the boxes that we were filling together in the lecture. So for proving of a theorem, and most important for practical aspect of the DFT procedure. So what have we accomplished in the last lectures? We did agree that density is like a fingerprint of a criminal, and it determines external potential, and in principle it gives the function and molecular Hamiltonian, which allows to find any one and only one, and it helps to find anything about the system. And the second theorem is that if we know the absolutely correct density, and if we know the equation for the conversion from the density to total energy, then any density which deviates from the correct density, rho 0, will increase the energy. So correct density gives minimal energy of the system. So this is a flowchart that you have placed together as there is a background noise, and let's try to mute microphones of everyone who is not speaking. If you need to speak, put them on backwards. Okay, thank you. So this flowchart is what software is doing, and when we use the red box as a unit to compute the total energy, one can plug it into the flowchart for geometry optimization and for molecular dynamics. So this is the review of useful things that we did. Now, before we go to a new material, if there will be time to go through new material, I want to give a couple of comments which are not academic abstract part of the theory. It's more related to practical aspects. So when we were finishing Hartree-Fock theory, we derived this equation. Tomorrow in the lab, there will be time to practice this equation. And I would like to bring it up to your attention, and I'm going to jump a couple of slides back and check who will be presenter of this subject. Steven. So this is most important equation for Steven, but for the rest of the class as well. So what does this equation show? If we promote a system from ground state to excited state through optical excitation, it means we are going from absolute ground state to a determinant where electron is promoted from orbital I to orbital J. And probability of such transition is expressed as integral over orbital I and orbital J with electron position operator between them. So this construction is referred to as transition dipole moment. I want to bring to your attention that position operator is a vector, therefore transition dipole is also a vector, so it has three components. This transition dipole is will be computed for each pair of orbitals, where one orbital is occupied, another is unoccupied. If the transition dipole is 0, it means optical transition is impossible. If it is large, it means it is possible. Also, the optical transition will happen if the energy offset of initial and final orbitals is in resonance with the frequency of the incident light. In the next lab, we are going to use output of WASP and compute a table in the a file called Oscillator Strengths, which will include the pairs of orbitals I and J and 3 components of this transition dipole vector. There is a so-called Fermi golden rule. Please, now I do see your faces. Please give me signs if you have heard about Fermi golden rule before. Okay, please give me signs if you did, or if you didn't heard, if the Fermi golden rule is something very new for you. Okay, I'll briefly cover it and maybe send a link, or you can find it in the Wikipedia. So, in case we do have a quantum process that brings us from one state to another state, and there is a probability of this transition. Not probability. If there is a matrix element corresponding to this transition, then probability will be corresponding to the matrix element of this transition squared. And this concept, which I kind of simplified, but not much, it is called Fermi my calligraphy is not good. Golden rule. If we try to apply Fermi golden rule to this matrix element of transition between initial and final orbitals under optical excitation, we will come to the square of this transition dipole. And the square of transition dipole is referred to as oscillator strength. Please give me signs if you have heard the expression oscillator strengths before. Salim should have heard about it. Can you please put your microphone on and tell your share your memories? What is oscillator strengths according to your? No one except you can help us. Just any general directions. Please put your microphone on. We do not hear you.
Okay, it's on. I'm not sure. It looks like a delta function. I think I forgot. But I've heard about it.
Which area of science is it related to? In which circumstances did you hear?
Sorry, I didn't hear it. In which circumstance?
Yes.
Do we have it?
Yeah, in which circumstances did you hear about it?
Oh, in the excitation of like optical excitation, for example.
Right. Okay. Yep.
And the transition between the ground state, like you said, to the excited state. And yeah, that's what I know, but
okay,
not in much details.
It's good. Please put your microphone off.
Okay.
So the concept of oscillator strengths was designed by spectroscopists much before quantum mechanics and quantum theory and any computations were set up. The experimental spectroscopy was existing maybe 100 years before quantum theory, and researchers were measuring absorption spectra of molecules and materials and making an observation that at one wavelength material does absorb and at another one it does not. And 100 years ago there were no quantum theory. There were only concept of harmonic oscillator, when something oscillates. And the incorrect ancient theory was that in any molecule something is oscillating in resonance with exciting electromagnetic field. But one oscillator is stronger, another oscillator is weaker. Therefore, absorption spectrum was related to the strength of each oscillator. So it is a historical name. Okay, so oscillator strength. And more modern vision is that it is computed for this matrix element between orbitals, between wave functions, and one can compute it literally. Now, what do we do with this oscillator strength? I wouldn't be surprised to hear that all of you know which equation is used to generate density of states. Density of states is using subtraction of energy of free parameter energy and energy of given orbital as argument of delta function, right? If we are speaking about absorption spectrum, then we do have three arguments under delta function: frequency of light, energy of final orbital, and energy of initial orbital. So if the frequency of light converted into energy by Planck constant is equal to the energy offset between orbitals, then light can promote electron from this orbital to this orbital. So this delta function does set a resonance condition. If h bar omega is equal to ei minus ij, ei minus ej, then this transition is possible. But in addition to this concept, we already also multiply this resonance condition by oscillator strengths. So there are a lot of transitions which are in good resonance, but they do not contribute to absorption. They are so-called dark transitions. So oscillator strength is needed to separate bright from dark transitions. And then in order for a material to be able to absorb light, one needs two conditions: resonance and brightness. So only those transitions which are in resonance and which are bright, which they will contribute to absorption spectrum. And this is what we are going to get in tomorrow's lab. We will get a table with number of orbital, initial and final, and then at the end of the table there will be three projections: dx, dy, dz for the oscillator strengths, and the third column will be given oscillator strengths. So for this pair of orbitals, this transition will be bright. And then there will be some practical tools to convert this information into spectra. So this little explanation is just repetition of what we discussed. So we are exploring resonance condition, which is okay at certain wavelengths. And then we use oscillator strengths as a height of a peak. Therefore, absorption will be stronger or weaker at certain wavelengths, at certain transition energy. And the spectra that we are going to generate will look this way. We will do them both in as function of transition energy and as function of wavelengths, because some of us, for example, Salim, may want to compute spectra in nanometers and compare them with experiment. Okay. We are almost over time, but let's speak a little bit about lecture material. But I assure you that the information about absorption spectra is more important than actual abstract lecture material. Okay, so we went over the slide. It is how density, local density approximation works. So what do we see? The slides that I'm going to show now are not related to what we will be doing tomorrow. It will be related to the stuff that we will be doing in a week from now. So maybe I will need to review it anyway. So there are several conditions, several circumstances when one needs so-called open shell computational models. Open shell means that orbitals are filled. So typically we have paired electrons, and open shell is when there are several orbitals which do have unpaired electrons. This modeling is needed if you want to computationally describe electronic paramagnetic resonance, or if your material is very magnetic, or if your material maybe not strongly magnetic, but it explicitly includes transition metals like iron, cobalt, copper. So then the separate description of electrons with spin up, or sometimes we call it spin alpha, and electrons with spin down, we often call them spin beta, are needed. So I apologize for our labs and lecture materials being a little bit behind each other. What we are describing now will be implemented in a week from now. So I'm hoping on your good memories. So do you remember equations that I'm showing right now? So I was very much positively surprised that the mathematically abstract homework was completed absolutely perfect by everyone. Although a lot of class attendees were complaining that they do not have sufficient math background, the homework on the spin operators was completed the best. So I think everyone in the class has a mathematical talent to derive equations. So let me bring up quickly remind what I'm showing here and why it is needed for magnetic materials and for open shell calculations. The single, if we do have electron that can flip spin, it can be in state up, alpha, and it can have spin down, beta. Or sometimes people call it plus 1/2 and minus 1/2. So those plus 1/2 and minus 1/2 are quantum states. There are two quantum states, and mathematically it is basis, same like for two-dimensional vectors. And spin state, if you have electron that is localized in one spatial orbital, but we allow for this electron to flip the spin. We reduce overall space only to two discrete states. And one needs quantum states that may jump, that may describe transitions between spin up and spin down. So the operators operator S plus converts from down to up, operator S minus converts from up to down. And I remember my positive feelings of everyone successfully completed this homework. Now, if we perform linear combinations of this S plus and S minus, what are we going to get? We are going to get 3 components of magnetization, which is induced by this spin. So even like if spin is, if we select a direction in space and our spins can align only along this z-axis, up and down, there is a probability that the spin will be in a superposition halfway between up and down. And then it will have transversal direction of magnetization corresponding to the spin. So if we add together the spin creation and spin annihilation, it will be Sx component. If you subtract these operators, it will be Sy component. This is very much needed for nuclear magnetic resonance and for electronic paramagnetic resonance, where magnetization may have components in x, y, and z directions. Between these Sx, Sy, and Sz operators, there is and magnetization, there is a proportionality factor. There is a gyromagnetic ratio, G. But in principle, these S operators are already related to magnetization. It is quite interesting and useful to check how the expression for Z component depends on this S plus and S minus. So one needs to practice S plus and S minus first, and then S minus and S plus second, in order to get this SZ component, and it will have the only diagonal elements. So if spin is up, then expectation value of SZ will be plus 1/2. If spin is minus, completely beta in a second state, it will be minus 1/2. So this operator decides where we have spin alpha or spin beta. So if we do have spin index, spin degree of freedom, then instead of orbital that is, instead of molecular orbital which is just listed by its number and has different energies, we may need to explicitly add spin index to molecular orbital, because orbitals with spin up and spin down could be different. I think we partially covered it in the Hartree-Fock calculations, and someone already presented it on our presentations, right? I have forgotten who was it, but I think we were, Salim, you did? Okay, good. So we were plotting spin-polarized orbitals. Okay. I think we will not go over the whole material, but we will be going slowly but surely. So what if we have two orbitals? One orbital with index I and component alpha, and another orbital with component, it's also I, but component beta. So it's same orbital, but up and down spins. They can look differently. what can we do mathematically with these two orbitals? We already know from all our derivations and practical aspects that orbitals themselves are not quite related to observables. One typically, for all operations, need to make squares of orbitals, multiply them one by another. And if our orbital number I has two components, alpha and beta, it looks like two vectors. It looks like one vector with two components. And this vector can be multiplied by itself in a scalar form, which will give alpha times alpha plus beta times beta. Or one can multiply this vector on itself in the opposite way. Instead of row by column, one can multiply it column by row. So in first case, we will get a number. In second case, we will get a matrix. So let's just practice ability to concentrate on equations and see what will be this matrix. So if we multiply column by row, it will be matrix 2 by 2, and the diagonal elements of this matrix will be phi I alpha times and this another diagonal element will be phi I beta. So if we compare this number and summation of these two diagonal elements, we will see that they are the same. If we add these two things, if we add diagonal elements together. It's just an interesting observation. Another observation, what if we want to give a shorthand notation for this 2 by 2 matrix? I can skip the index I, and then there will be elements row alpha alpha, row alpha beta, row beta alpha, and row beta beta. And then the scalar in the scalar product will be sum of the diagonal elements, row alpha alpha plus row beta beta. I'm about to finish soon. There will be no time to go over all slides, but how to interpret this row alpha alpha and row beta beta. Row alpha alpha is a probability that this electron has spin up. Row beta beta is a probability this electron has spin down. Summation of probability up and down should give 1 if we integrate it. Like if we integrate probability that electron has spin up and that it has spin down, it should give 1 because we are speaking about one electron. But if we do not perform integration, then it will be density of the electron in the orbital number I, no matter which spin it has. Right? Summation density of electron in given orbital with spin up and spin down. It will be partial density for given orbital. What if we subtract these two components, row alpha alpha minus row beta beta? this will be, just in case, if our model is closed shell, if you do not have unpaired spins, then subtraction of rho alpha alpha minus rho beta beta will be 0. So it will be non-zero only for open shell models. So this subtraction of spin alpha and spin beta is a measure of is one of the measures of magnetization of the system, of if the system has unpaired electrons. And this matrix in the lower right is mostly complete information about spins. So it will have out of these numbers rho alpha alpha, rho beta beta, rho alpha beta, rho beta alpha, one can tell everything. Total density, one can find subtraction, spin density, and one can find projections on in all three directions. I suggest that we finish at this point because we need to boost our practical skills and a little bit delay abstract academic part. And let me declare this one as end of the lecture 21. See? And I'm going to stay online and answer questions, if any, but with this I would like to announce completion of this lecture, and anyone who needs to follow the schedule is welcome to disconnect and depart.
Dr. Dimitri?
Yes?
In the MOBA-X term, I'm unable to access the shared directory. Is there a problem with the software installed in my computer, or I don't understand?
Just a second, just a second. So, please, I'm going to repeat what I hear, and please correct me if I'm understanding it wrongly. So, you are able to download, install, and open MOBA-X term.
Yes.
You are able to connect to a Photon server.
Yes.
But when you are transferring files, you cannot find where are these files on your local computer.
After connecting to Photon, we access the shared directory at first. I'm unable to access that. It just keeps on, it doesn't display anything. I write CD shared, but then nothing comes up.
Okay, okay, okay. I will explore and email to you what I find. It shouldn't be this way.
Okay, thank you.
I even if there are no more questions, I can even do it as we speak.
Okay.
Does anyone else has similar?
I had the same problem. I emailed you, but didn't get a reply.
Oh, sorry. It looks like a little slow. Yes. I will email to other researchers who are using Photon. It could be just too busy, and intensively writing files.
Okay, Dr. Kalim?
Yes?
Last lab session, you gave us, for instance, a comment to save some lines after E Fermi. So there were some numbers between occupied and unoccupied, for instance, 2 and 0. But for the comment that you put in the homework 8, you mentioned increase the NSW to 100.
Mm-hmm.
So after increasing to this value, we have several E Fermi in the outcome file.
Okay. I like your question very much. Use
so,
the,
but between
use
so the question is okay,
use the last one.
Okay, but between 2 and 0 also there is several other numbers, decimal numbers. So how could we find the occupied and unoccupied HOMO and LUMO here?
So Amir is bringing up an important practical question, which is very relevant to modeling of metals. So if your model is not dielectric, not semiconductor, but if it is a metal, then occupation of HOMO is less than 2, and occupation of LUMO is more than 0. This typically happens when this energy offset of these levels become small.
Okay, but how to determine the band gap distance? We use the 2 and the...
Okay. I got the question. So if you type grab number of electrons, grab number of electrons out car. It will show number of electrons, right?
Yes, the granular.
The number of HOMO is number if you do not have spin, if it is closed shell, the number of HOMO is number of electrons divided by 2. Does that make sense?
No, can you repeat it again, Dr. Kalim?
I'm going to repeat, do not worry. For each model, there is a certain number of electrons that are contributed from each atom.
Right.
One can manually count it just by analyzing each element, or one can simply inspect the outcar by typing this command grep NELE space outcar. One is getting how many electrons are in this model. Now, if it is a closed shell model, then number of HOMO is equal number of electrons divided by 2, right? So if you explore energy of orbital, which is n divided by 2 minus number of orbital it will show up in a second. I need to complete typing. So last thing that I typed, energy of orbital with index number of electrons divided by 2 plus 1, which will be LUMO, minus energy of number of electrons by 2, which is HOMO. This will be the gap. Okay. And typically, one needs this trick when the gap is approaching 0. It means that the gap is smaller than a fraction of electron volt comparable to thermal energy, like 0.02, 0.01 electron volts. If your gap is open, if your gap is of the order of couple of electron volts, 1, 2, 3, then you do not see this circumstance. And in the homework, we are considering the dielectric. Titanium dioxide is known to be dielectric. So if you are getting gap close to 0, it could be a sign that there could be some additional error in the process of building model. It doesn't, do not discard your results, keep analyzing them, but it's a little bell, little red flag that something may went not in a way as it was designed. Make sense?
Yes.
Yeah.
But for the next step, when we create the dual S, use the dress dual S normal command, there's still an error.
Can you send a screenshot or maybe show it right now by sharing screens? Sharing screen.
No, it's it's in my desktop.
But you can share screen, and then we all will see what this problem. In communication software, on the bottom, there is a symbol that tells share screen, and then you will show what you're doing to the whole class. I hope there are no secrets, and you'll show only work-related thing.
Yes,
Johan,
but
that's the picture that you send me, or
yes, I sent you. Yes, okay, I sent you through the Slack.
Let me share the screen.
Yes.
Can you see the screen, Dr. Kian?
Not yet. After you click share, right now I think my screen is still shared with everyone. You need to click share screen, which is like symbol of display. And then if you have more than one displays, it will ask which screen to share, and then you need to confirm it.
What about now?
Yeah, it works.
So this is the
okay
picture that Johan shared me.
Very good, very good. So this least directed input-output syntax error. This error will happen if the number of states that you did declare. So on the top of this writing, you're answering number of states 20, right?
Yes.
The script is trying to read the file states, and it tries to read 20 records from there. If the file states has less than 20 records, the code will give an error. So try to open the states file and check that it has 20 lines, and you are not counting any spaces. All 20 lines should include the energies of orbitals. If number of lines in the file that you called states is less than 20, then use this number by running the script. So the number that you report to the script and actual number of records in the file should be consistent. If they are not consistent, the code reports an error.
Okay, I checked the What's the name? Status and the number of bands is 20. So the value should larger than.
Just in case we may get disconnected.